Okay, let's do one simple one today. What we're gonna try to do is we're gonna try to approximate vertex cover. Okay. Now how we're gonna do this is we're going to try to of course in polytime. Right. So the intuition behind all this is that like for the last 2 weeks we've been talking about NP complete problems. We've been talking about how it's difficult to solve them. The intuition behind why it's so difficult actually it's kind of like because if you want to find a vertex cover, it's not that you can't, right? For example, if you want to find an independent set, it's not that you can't. It's that you want to find like a really small one. It gets very challenging, especially if you want the exact value itself, right? Like if you imagine like for example having like a really big graph, like I don't know, 1,000 or like 5,000, like 100,000 nodes, and you want to find what the exact value is. It could be some like I'm not saying like it could be some really screwed up value. So like like we don't know how that's gonna pan out. But it's kind of like when the intuition is that when you want to get the exact value, there's a lot of details in the graph that you might need to deal with. And intuitively, that's what makes the problem so difficult. Because when you have like that many nodes, right? And any choice you screw up, like in terms of like like perhaps including something or not including something, really sort of like like makes the like, how would I put it? It kind of just makes the problem really difficult overall. Like you can imagine like in 3SAT, for example, one thing that you could try is to like like try out different assignments, and you would say, okay, let's say I tried this assignment first before trying that assignment, that sort of thing, right? You could like even like say let me set xi to be true first and then see what happens, that sort of thing, right? The difficulty is that when you have like 1,000 or like 2,000, 5,000, 100,000 of these variables, if you make one slip up anywhere, right, it kind of screws up the entire thing. So the same thing kind of happens here with vertex cover. If or like with independent set, all these problems kind of have this where like if you make one slip up with like for example, I want to find the vertex cover. Let me try slowly putting vertices into my cover. Like let me try slowly covering edges, right? The moment you make a single mistake, as to like how you sort of like do this, right? How you pick put items in your set, it really just throws you away from being optimal. You could be one away from optimal, you could be two away from optimal, right? But like all in all, in the last 2 weeks, we're saying that hey, as long as you're not optimal, or like sorry, as long as you don't hit that value, right? We can't allow this. We would say you're doing it wrong, right? So in general, we say a problem is difficult. The nice thing is that like we kind of live in a world where even though these problems are difficult, at the very least we can find approximation solutions for it. So what that means is that like if if you're okay with, let's say, a 5 million node graph, right? You outputting something that is like like close to optimal. So let's say the true vertex cover, let's just say was, I don't know, let's say like 500 nodes or something. In this really big graph, right? You would be outputting something that's at most 1,000, right? You when So what I mean by this is that like when I say 1,000, I don't mean that like when you output 1,000, that the vertex covers of size 500. Like the vertex cover could be sized nearly 1,000 as well. But the point is that in the worst case, you're only 2 times off. But you don't know what the exact value is, right? You could be really close, you could be really far, but the point is that like the furthest you'll be is 2 times at most the solution size, right? So the idea is that you could think of like how sometimes you don't really need exact solutions. You could like the motivation at least is to say that like sometimes maybe if you have like a rough solution, it's good enough for whatever you're trying to do, right? Like maybe this is like a routing problem, where things can get very NP complete, for example, and your boss tells you, okay, fine, like I get that it's difficult, but maybe we can come up with something close, right? So we can still try to save as much as we can. Just because there is no like optimal solution doesn't mean that you can't come up with like a solution that is, kind of good, right? So for today, let's try to approximate vertex cover using polytime. So what I'm going to want is a 2 approx. Okay, so when I say something like, for example, if it's a 2 approx, right, the first thing you need to ask yourself is this a minimization problem or a maximization problem, right? So in the case of vertex cover, it's a minimization problem. So what a 2 approx would mean is that this directly translates to saying the output of my solution should be at most two times the optimal solution. Right? So what this is trying to say is pretty much just that, like, I mean, this is just like it in English. It's just, I mean, this is for minimization, by the way. So you know, if you want to minimize something, you know, your solution can only be larger than that, right? And it should not be like 2 times, like, you know, it should be like at most, in the case of a 2 approx, it should be at most 2 times larger, right? So on the other hand, if, like, for example, let's just say that there's a maximization problem and you wanted a 2 approx, right? What this means is that you like, you know, the larger the solution, the better, right? But you can only get up to about like at least a factor of half of it. All right, so that's what we would mean by maximization. Let's talk about minimization here. So okay, so the intuition on how we're going to do this is that we're going to try to find something that guarantees us a vertex cover. Okay, so what I mean by this is that you're going to have, we're going to try to like find a set of edges and we're going to try to cover them. Okay, and this is going to constitute a vertex cover. Okay, but just because it's a vertex cover doesn't mean it's like the best vertex cover. It just means it's a vertex cover. And what's going to happen with that is that we're going to say this thing is not very far away from the truth. Like, it's not very far away from an actual vertex cover. Okay, so we need to use something called a matching. So a matching is pretty much just a set of edges that do not share share an endpoint. Right, so like, for example, if I give you a graph, let's say I drew it out and it kind of looks like this. Right, let's start throwing stuff into the matching. Let's say, for example, I could throw this into the matching. After I throw this into the matching, I think I can just throw this into the matching. That should be good enough. Right, so like, for example, this would be a matching, right? Like, if I put these two red edges inside the set, that would be a matching because they don't share any endpoints, right? Like, if I added anything else, I think that would be an issue. Like, if I added this, that would clearly share one here. If I added this, it would share one here. Yeah, and I'm pretty sure anything else here would share one with this edge here. Right, so again, a matching intuitively is just they don't share the same endpoint. And one of the intuitions for why a matching is good for us, right, is because you kind of want to spread out your edges. You kind of want to make sure they don't share endpoints, because if you think about like trying to use this to find a vertex cover, right? So you have like some edges, right? Maybe like this. Okay, and perhaps, you know, you would want to, let's say, take this one. Let's just say, right, like you pick some edges like that, and then you would say like, okay, let's try to cover the entire graph using these edges, right? And what we're gonna do later on is we're gonna use both endpoints, but for now the point is that, like, if I use both endpoints, then I would have to like do this funny thing here, and I would say I propose all these purple nodes as covers, right? The intuition here is that this purple node here is wasteful. You actually don't need it, you know, that sort of thing. So, but like, if you spread out your edges, you know, you can kind of like have as much of a coverage as possible. Then that's the intuition. And when you do that, the idea is going to be that then if you use both endpoints to propose for a cover, it will not be very distant from a vertex cover. So that's the idea. Okay, but first we need to find a matching. So let's do that. So I propose this algorithm. And the way that's going to work is pretty much just for all E and E, like fix some way to iterate through them. Okay, and then what you're going to do is that if edge, so just pick some edge, like just pick an edge. You don't have to be random about this. Like, when I say pick an edge, it just means like pick it via like your favorite method or whatever. There's no coin flipping involved here. Pick an edge, any edge. Okay, and then just add it into a set S. Okay. Now what's going to happen is that after you do this, right, you need to remove all adjacent edges to it from E. You can use a hash table to do this, whatever. right? The point is get them removed somehow. Like when I say hash table remove it, I mean like you just tell the hash table, hey, this edge is removed. So if you ever look at it again, don't, that sort of thing. So what's the idea here? The idea here is that you're going to pretty much just take any edge you want. Like I know there's really no way to discern between these, and then just dump them into a set, and then like whatever is adjacent to it, just remove it, right? So you then just like keep doing this until no more edges. Okay, so of course, this intuitively this tells you that you should be getting an independent set, right? Sorry, a matching, right? Because the reason why this should give you a matching is because okay, so I want to say like all the edges are going to be okay. So the first thing is this definitely gives you a matching. You definitely will not have two edges in the same set, right? That share any edges, share any endpoints because you're going to remove all of the adjacent edges anyway, right? So no endpoints are going to be shared, right? The next thing that I want to argue is that any edge is going to be adjacent to any edge is going to be either in set S or adjacent to set S. Okay, so you still have to prove this, by the way. Like I know it looks obvious, but in the exam, if they ask you to prove it, you can't just say, hey, by definition of the algorithm, right? So the way that you want to prove it is by saying how, okay, so basically we want to say there's only two sets of edges, the ones that are in set S, right, or the ones that are adjacent to set S. Right? So assume by contradiction that that's not the case. Assume that there exists some edge, there's some special edge that's called that G, right? Let's say this edge G is not in either case, so it's not in S and it's not adjacent to something in S. Well, then by definition of our as in like now you can say like by definition of our algorithm, we know that this edge was not removed, right? So like this edge could not have been removed. Right? So what should our algorithm have done? It should have considered it at some point and added it into the set S, which gives us a contradiction. Right? So what this means is that any edge should really only be of either two cases. It should only be like either adjacent to S or in set S. Okay, so good. So what do we know now? We know that basically we have some set S. This is a matching, right? It's going to contain some edges, and the rest of the edges are adjacent to it, right? So we can sort of like view it as like this set S just has like all these things hanging out, and like all these are the remaining. So like all edges in the graph are either outside here, right next to it, or inside S, right? So this is pretty good for us, right? Because then what happens now is that if I sort of just like started, so let's just say my matching kind of looks like this. So let's say purple means it's inside set S and green means it's not. I could have something like this, right? Maybe like that. Okay, so the intuition now is going to be that if I somehow have like this matching, right? What I'm going to do is I'm going to just include both endpoints of my of all the edges of all the purple edges, which means like for every edge that's in my matching, let me just dump both the endpoints into into a cover, a proposed cover, right? And the idea is going to be that this should cover everything, and it shouldn't do too bad of a job at it. That's the idea. Okay, so let's think about that. Why is that the case? Well, first of all, like we should be concerned whether this is even a cover in the first place, right? Because if this is not a cover, then what's the point of considering it? So this goes back again to like our observation that like every edge is either adjacent to S or in S, right? So think about all the edges in S. Are they covered? Why, yes, they're covered by definitely both of the endpoints, right? Like we've included both of the endpoints in the cover, so it has to be it has to be covered, right? Now, what about the green one? Now the green one has to be covered as well, right? Because what's going to happen is that even though they were not part of the matching, right, they must have been adjacent to something that was part of the matching. So at least one of the endpoints is going to be included in the covering set, right? So okay, so we know that all edges are either adjacent to S or inside S, and we know that all the ones that are inside S are definitely covered. We know the ones that are adjacent to S are definitely covered, right? So in other words, like what you should see is something like at least something like this. Sometimes maybe this edge actually loops back and you have to cover that as well, right? Like in the case of this one, for example, both of the endpoints are actually adjacent to S, right? So this gives you a cover, right? So the only question becomes, how good is this cover? Right. Intuitively, I think you can already see based on this one, there's a bit of a waste going on here. So like, for example, I think you don't actually have to include this node here. This node here doesn't have to be part of the cover. I think this node here doesn't have to be part of the cover as well. Yeah, that's right. So that you could have excluded these two, right? So like, this is not an optimal solution, right? Optimal solution would probably be like this one, this one, this one, and this one. So I think we're like, instead of a size 6, size 6 is our solution. We have, but the 4 should be optimal. I think 4 is optimal here. I think for this graph should be easy to see that 4 is optimal. So we're kind of close, but we're not there, right? Like close but no cigar sort of situation. Okay, so we know it's a cover at least. So what that tells us is that, and remember the size of our proposed cover right now is 2 times the size of S, right? So we know this. We know two of S is at least C. Okay, we need to show that basically. So let me show you what this is on the number line right now. So if I plotted out a number line, and let's say 2S was here, right? I know C is somewhere here. Oh, sorry. That's not a very straight line, but I know C is somewhere here. Okay. Now, the scary thing is that if you only have one inequality, last semester I've actually had students ask me this, but if you only have one inequality, why isn't this good enough, right? Why doesn't this show me what I want? Like for example, hey, I know C is at most 2 times of S, right? The thing is that like C could be really small, right? And S could be really big. So let's say S could be something like, I don't know, it could be like log V, for example, let's say, like depending on the graph, right? It could be like maybe V over like 20, or it could be, I don't know, square root of V, something along those lines. I don't have a good guarantee for you, right? I just know that it's like some value. It's probably not square root of V, it's probably not log V. Like, okay, I guess it depends on the graph, but the point is that it could be any of these values, and C could be really small. I don't have a guarantee, right? C could be 1, C could be 2. I mean, okay, C can't be 1, like that would be a bit obvious, like to disprove that. But C could be like, I don't know, 20. C could be like, let's say, I don't know, log V square, like square root of log V or whatever, right? The point is that C could be really small. Like if I put that in green, C could be really small, right? And your proposed solution could be like really big, right? And there's not really a good ratio between these two now. So you kind of need to limit how far back intuitively. You kind of have to limit how far back the cover can go, right? So in other words, what we're trying to say is that you have to probably have a left bound as well. You kind of need to draw a line that says, okay, you as the cover, you can't really be that far back, right? Like you can, like the best the cover can be is like somewhere here, let's say, right? So my solution is going to be here, and your solution is going to be like at most some distance away from it. That's how we like sort of say, hey, you're not, we're not really far from the solution, right? I mean, of course, like like you could tell me, hey, we never know, right? Maybe the cover is like actually somewhere around here. That's true. That's fine, right? But the point is that without a guarantee, like we kind of have to assume the worst case, and the worst case is like whatever bound we get, right? So like without a left bound, without a lower bound on C, right? We're going to we can only assume that it's going to be like really far back, which means that our approximation is a really poor one, right? So we still need a left bound. Now, like I think I mentioned this with my colleague in the previous tutorial, but basically, like we don't really have good advice, or at least I don't really have good advice on how to sort of deal with approximation problems. Because like if this is DP, if this is amortization, I've already given the advice like, oh sorry, not amortization, but like randomization. Or you should try to think of everything as like indicator random variables. Try to break them up to sums. At least you have somewhere to start, right? For approx, I don't really have good advice for it. I think it's really just you need to just whack it, like. Yeah, because I've never really had to deal with that many approximation problems myself, so I can't really go what's beyond what was taught for me. Like for the previous ones I did, but for this one I really can't. Wait, so where was I? Right, so we need a left bound. We need to know how small how good can a cover be, right? Sorry, this should be S. Okay, good. So let's talk about that. So one thing to notice is this. So let's go back to the graph, right? So let's say purple edges are in the matching and green edges are not. Something like this, perhaps. Something like this, let's say. Okay, so let's say that we forgot about the green edges for now. So let me just copy out the matching edges. Okay, the first thing for you to note here is that these edges actually tell you at least what the cover size needs to be. So you see, like, if we forgot about the rest of the edges, right? And I just looked at the matching set alone, I know that each of these guys needs at least one edge, one node to cover it, right? Because and they don't share endpoints, right? So the thing is that you can't recycle nodes here, right? Like what I mean by that is like to say, okay, forget about the green edges. Let's just cover only the purple edges for now. How difficult can that be? How much do I need, right? How many nodes do I need? Well, for each of these guys, I need exactly at least one node, right? Like I mean, I don't know how I'm gonna color it. Like let's say I could, I'm just saying that like okay, between these two endpoints, at least one of them has to be taken. Between these two endpoints, at least one of them has to be taken. Between these two endpoints, at least one of them has to be taken. And between these two endpoints, at least one of them has to be taken. Right? So that's kind of what that looks like. When I color this, I don't mean I know which one, right? I'm just saying at least one. Okay. So the reason why this is the case, is because they don't share endpoints. So you can't sort of like use one node and like recycle it for two edges. So every edge here needs to at least have one edge covered, right? Now, of course, if I add in the green edges, right, the story is a bit different. Like the question is, does it make the problem any easier? Like, can I somehow reduce nodes that way? Well, no, right? Because if I add in more edges, that only require like that just might mean that I need to add in more nodes to the cover at the end of the day, but never reduce it, right? Because like if you add in more edges, that's just having more to be covered, right? Perhaps like some node that you add here could already cover that edge, that's fine, right? But there is no way adding an edge would allow you to say, okay, I don't need this node anymore, right? Like to cover the purple edges. Okay, so what I'm trying to say is that what should the size of the cover be at least? We know it needs to be at least S, the number of edges in the matching set that we got, right? So what does this tell us? This tells us that like, okay, so let me clear this out. So what this tells us that if I drew the number line again, okay, there's going to be a 2S here, and there's going to be an S here, right? Okay, and what's going to happen is that basically, your solution is going to be here, right? You propose a solution that's going to be here, okay? And again, because we don't know where the vertex cover size could be, for all we know, it's like near 2S, right? Like maybe it's not even exact. Like you could be lucky and it's exact. Is there a case where I don't think you can be exact if there's a vertex cover that's exact? Oh, I guess you can, right? So like for example, a graph that kind of looks like this. Then if you're lucky, right? Like you pick this middle edge to be in your oh wait, sorry, I forgot to mention. So it says no, I already did mention it. So what we're gonna do is that we're gonna take all these purple edges, right? The proposed cover that we're gonna have is that we're gonna take all these purple edges and we're gonna dump both of the endpoints into the cover and propose it as our cover, right? So you can see there's clearly a bit of waste, but we're gonna prove that it's not so bad, right? And so this was saying, okay, whatever edges are in our matching set, right? We just dump both the endpoints. So since every matching set has like if there are S edges, then we're gonna put two S nodes inside the cover, right? That's how we got that C is at most 2S, right? Because C is the optimal cover, 2S is a cover, so 2S as a cover has to be at least the cover size, right? So then after that we said, oh, and the cover size has to be at least S because all the purple edges have to at least be covered, right? And then we're saying, okay, so basically what I'm saying is that right now on the number line, let's say there's S and 2S, right? Okay, I was asking myself whether it could be possible that the solution is exactly equal to 2S. I think that's actually true. So if I had a graph that kind of looks like this dumbbell thing, then if you were lucky enough to somehow pick this edge right here, then you'll be good, right? You'll be good because then you would just include these two endpoints, like this one and this one. And I think that covers all the edges. Right. So this gives you this is optimal. So like you could be lucky and you can make it optimal. That's definitely possible. Right. So my point is that like the solution could definitely be like, like your number S here, right, could actually be like 2S here, could actually be the optimal solution. That's completely possible. All right. But like you know that as your solution is stuck here, and as the vertex cover the actual vertex cover solution like size could move back, right? Like it could actually be here instead. We don't know, right? But so like the further left it goes, right? Meaning like the smaller the vertex cover is, the actual vertex cover size is, right? The worse your approximation, right? Because that's the further away your solution is to the actual solution, right? But we know that because the actual vertex cover size is at least S, right? It means that like the furthest left that it can go on the number line intuitively is here. Is like, so in the worst case, right, the vertex cover size could be S, right? Can I come out with an example where that's true? Yeah, so like for example, just for a single graph, right? Like a single like that. Like sorry, it's a single edge, right? So then like the vertex cover size is 1, but we're going to include both. We're going to include both in the matching set, and then we'll call it a day, right? So it is possible. It is possible that a vertex cover size is exactly S, but the output of our solution is 2S, right? But can a vertex cover size be smaller than S? The answer is no, right? So we know this. We know that the output of our solution, right? The actual solution lies between the output of our solution and like this value right here, right? So what do we know? In the worst case, VC is S and the output of our solution is 2S, right? So in the worst case, we're kind of like 2 times the vertex cover size at most. All right. So at the end of the day, you really just want to find inequalities that sandwich your actual solution. That's how I would put it. So this is how you would approximate vertex cover. Then like we still, I mean, if you need to prove that it runs in polynomial time, you could just say like it's probably E squared. Can you do E log E? You might be able to do E log E. I think E log E is possible. So you can think about how to do this in E log E. I'm pretty sure E log E is possible. But the dumb solution will be E squared, right? Just go through all the edges one by one. Remove them if you need to, so on and so forth. So that's that. What else do I have to say? Let's see. I think that's about it. And the reason why this recording is much faster now is just because I'm talking to myself. So there's like, I'm not trying to, I don't have to give time for you guys to think, because you guys can just pause on the video. So yeah, thanks for stopping by. Let's see, stop the recording now.